opportunity to present here. I hope to advertise a tool for the construction of finite models, finite structures that is very aware of symmetries that are involved in such tasks or can be involved in such tasks. Given the time constraints, this can only be, hopefully, an appetizer for you to look at the actual construction. That is rather technical, but I already talked about some features, some applications, some sort of strands in this on other occasions in this wonderful Simons Institute program. So thanks for all these opportunities, and now just sort of a short summary of some of the ideas that I hope some of you will find interesting and that may be looking for many more applications. So what do I mean by amalgamation? Well, it's a basic task of sort of fusing together two pieces in a single amalgamation step, and I'm looking at sort of extended processes of amalgamation here where you want to continue fusing more and more pieces according to some pattern. And this has to do with issues involved in local versus global consistency, but also local versus global symmetry. And in some of these areas, you're really looking for patterns that can be used in order to generate nice and symmetry-preserving solutions to such tasks. So this occurs in many areas, I would say, and I'm just sort of trying to give a very rough idea of where it could occur. I mean, synthesis and amalgamation tasks occur in hypergraphs and relational structures, in all kinds of decomposition or composition tasks. In model theory, you have homogeneity aspects that have to do with amalgamation, as many of you may know. In geometry and combinatorial geometry, you may think of, or also classical differential geometry, you may think of atlases and charge, where this fusion is really to glue together and bring together these local views in order to give a picture of the overall object, the entire manifold, say. Local and partial symmetries occur, of course, in logic. Model theory are very much partial isomorphisms are local symmetries, partial symmetries, and then sometimes you can extend them to global symmetries. Algebraically, this deals with groupoids or equivalently inverse semigroups much more than with the sort of perfect symmetry behavior that is reflected in a group. Then local consistency, of course, occurs in many places, ranging from databases, constraint satisfaction to possibly quantum information issues. And I hope to convince you that there is an underlying task that occurs, has some impact on many of these areas. And so think of a construction task like this. The specification that you have is a family of relational structures and a family of pairings between them that are partial pairings that tell you how a certain structure of type AS, say, wants to be identified partially according to some row E with a region in some structure of type AS prime for some other S prime. So at the purely combinatorial level, you would really have a diagram that says which kinds of structures you have. This is the index S and S prime of two such contributing structures in the family. And you have links between them, directed links here, edges, in a multigraph that would say, identify some piece of structure AS with a certain piece of a copy of structure AS prime, and keep doing that. Right, so, of course, for a problem like this, there's a canonical generic free realization that just sort of uses basically all possible walks that you can have in this abstract representation of the gluing pattern that you want to realize, and put a copy of the corresponding structure in the right place. So whenever you arrive on a walk at S, at little s, then you put a fresh copy of structure AS and identify it with the place where you previously were along this walk according to the corresponding row E that got you there. Right, so this I wanted to note pictorially, semi-pictorially, by this notation here. You take something like a free product and factor out with respect to the identifications that are induced by the edges in those walks. Right, so this realizes, in the terminology that I want to suggest here, this overlap pattern that's given in the specification, or amalgamation pattern. It is free in a universal algebraic sense because you've basically not identified anything that did not have to be identified according to this specification. It's generic, but it's obviously always infinite unless your pattern happens to be finite and everything is fairly trivial anyway. Okay, so the question that I'm treating here is what are the finite analogues of this? Are there finite solutions? And if so, how do you get them? Based on what kind of background structure instead of this usually infinite monoid of all walks through the combinatorial representation of the links that you need to realize? Could you have anything that's equally homogeneous as this sort of canonical one? And can you control cycles or the behavior with respect to cycles that occur and make the whole thing interesting and potentially problematic with respect to global consistency issues? Right. Of course, in the free realization, you don't create any cycles, right? But if you want to keep it finite, then eventually you have to fold back onto yourself and their cycles, and then you need to discuss how about them, to which extent can you avoid them, to which extent can you avoid at least dangerous ones that would lead to inconsistencies. Right, so just for technical purposes, here's a very rough idea of what the actual definition of a realization in the general case is that we want to apply to the task of finding finite realizations then. So the overall structure that you want to construct should consist of lots of patches of these types that are given in the specification. So you can think of an atlas really in the sort of geometric sense, that you have patches that declare themselves as being isomorphic copies of AS for various of these kinds of structures AS that you have. In such a way that locally, if you have two pieces that declare themselves as copies of AS, one piece that declares itself to be a copy of AS, then for every one of those gluing actions that were provided or required in the specification, you really find something that overlaps with that piece there in exactly the right way, in the sense of how it's declared to be a copy of AS prime. Right? So you just sort of really have all the extensions, all the gluing operations in place where they were specified. This is the obvious part of the definition. This is the non-obvious part, which sort of tries to keep this safe and sane. Namely, whenever you have overlaps in this sort of atlas of pieces that declare themselves as copies of AS and AT, say, then the actual overlap in the resulting realization has to be forced by some composition of gluing operations that were really required. So there's no incidental overlap that would just have occurred because you put glue in places where it wasn't necessary to put glue. Right, so this second no-nonsense condition is something that goes in the direction of keeping this as free as possible, and also to avoid potential relational inconsistencies, and this is an aspect of global consistency that we're discussing here, because compositions of partial isomorphism are totally safe. Nothing can ever happen with respect to sort of inconsistencies incurred by just sort of stacking composing one partial isomorphism with another partial isomorphism with a third one. But if you look at unions of partial isomorphisms, so if you can get to the same place along different routes, then this is dangerous because the union of partial isomorphisms typically isn't one. Right? And that's where inconsistency, global inconsistency, can arise, even though locally the partial isomorphisms tell you everything is consistent. Right, so just because we're going to use groupoids, and you could equivalently use inverse semigroups as the kind of backbones, finite backbones that replace the monoid of all walks, which is infinite. In our constructions, composition structure of partial bijections can be described algebraically or combinatorially, either with a partial composition operation, in which case you get to inverse semigroups, or which is a total operation though, or you use exact composition where you only compose them where they match in terms of domains and ranges, and then you're talking about groupoids, which have a partial operation of composition because you can only link them where they match. Okay, so groupoids, but you could have used inverse semigroups just instead. So do for partial symmetries or partial bijections what groups do for global bijections, global symmetries. That's sort of a bit of a background why these structures arise. So in the context that we're talking about here, I want to use groupoids that are somehow designed to match the underlying combinatorial pattern of sites that you want to link and the way in which they are linked by identifications that are in the specification that I called I. This sort of I is, maybe I just put this here because you don't see it on this slide. The I was this structure consisting of the sorts of structures that you want to put, and then edges in a multigraph sense that link some of these sites according to labeled edges, and the labels tell you which identifications you locally want to perform. So here I use a groupoid whose elements, G is the set of all groupoid elements, come in different sorts, namely groupoid elements that take you from sort S to sort T would be one such sort of groupoid element. And then you have an associative composition operation, which can only link things that match together in the sense that here are elements that take you to T, here are elements that take you from T, and then you can combine them to get an element that takes you overall from S to U in this case. You have neutral elements, inverses. So it's like a group, but with a partial composition operation that respects sorts in the sense of taking you from here to there in this picture of sites and links between them. And we have designated generators here for this notion of groupoid that matches such a setting. They are labeled by the edges that you have here and, of course, respect that type. Right, and this is the potentially finite analog of the infinite path monoid that was used in the overall very generic but infinite solution that I talked about first. Right, and indeed, you can sort of perform a natural product with this kind of groupoid right away. Right? You use the groupoid elements as addresses for copies of structures of type AS or AS prime, and you link them according to this. If the address that you have here gets modified to become the address G times E for a generator E, then you link these two copies according to the row E that told you how to glue copies of this kind. Right? Question is, when is this a realization in the sense of this definition that I had? I mean, obviously, it always gets the first condition right. You always glue everything in places where it needs to be glued. But how could you maybe run into difficulties with respect to global consistency issues and have more identifications than are allowed according to this second no-nonsense or freeness condition that I have there? There are two kinds of obstructions, and they come from cycles in this groupoid structure that gives you the addresses of copies of structures that you want to put. And one is a simple one, namely you could have parallel identification requirements that come from some composition of actually necessary local identifications along a path W1 in the groupoid, path of generators you can think, path W2. They could link the same two types of structures with the same addresses S and T, but maybe they don't match, right? So you could even have here in the overlap sort of a clear mismatch, because only individually do you know this is a the two individual regions are bijectively mapped. The union of the two needn't even be bijection. So this is actually the easy one. The more difficult one is the one that really deals with potential violations of global consistency that come from the relational content in those structures. So here the domains and ranges of the corresponding identification paths are disjoint, so there happens nothing in terms of spoiling consistency with respect to elements, but you could spoil things with respect to consistency for relations linking these elements, because even though this is a partial isomorphism and that one is a partial isomorphism, their union need not be if, for instance, you have an arrow, a red arrow, and a sort of a red edge relation going upwards here and downwards there. Right? And the only way to consistently realize then these requirements would be to, well, at least introduce two more copies and unfold this twist. So as in if you've played around with this, maybe with as in a Mobius strip sort of situation where you have one twist which sort of forces you to bring things together in the wrong direction. But if you do the whole thing twice, if you unfold this cycle once, as it were, and do a double covering, then it all fits nicely. Right? And this kind of cycle needs to be treated. This would be a bad cycle if the red edges are present in those structures AS and AT. And we need to avoid these bad cycles. And the question is, what criterion of acyclicity is even the right one? Right? And it turns out that it's not generator cycles, as you usually consider when you look at Cayley groups, for instance, and just sort of want to forbid certain short cycles formed by generators. It's cycles that are being formed by cosets. And I'm sort of briefly trying to explain why. these coset cycles matter. First of all, what is a coset cycle? Here you go from one, you count as one step a transition that within a certain subset of generators takes you from G to some G prime. So this could be a long sequence of actual generators. So we're not controlling the length of that at all. It's just a certain kind of generators that take you there by however long a composition you like. Right, so why does this address the kind of danger that I sort of pointed out with this Möbius strip kind of twist situation? Right, think of this situation again. This is in terms of the desired amalgamation product that we produce with addresses G and GH for copies of AS and of AT. And we have one identification path this way in the upper part for the bluish pieces, or bluish elements A1 and B1, and another one along some completely different path of generators W2 that takes A2 to B2. Right? And now you could have sort of mismatched edges between these A1, A2, and B1, B2, as in the previous sketch. Now, if you look at the same situation in the groupoid that gives rise to these addresses G and H, G times H, well, then you can think of the generators in this bluish region here. Those are the ones that take A1 and maintain it as you compose these generators. So those are the ones that stabilize or carry A1, whereas the pinkish ones are those that carry A2. Right? And you see that here we're going along completely different collections of generators, namely those that carry A1 and those that carry A2, and come to the same destination. And this is exactly the kind of problem. Here I have this slightly enlarged, same picture as just now. Right? So think of the bluish part as consisting of being a coset here in this space of addresses in the groupoid, being a coset that is generated by all those generators that carry the element A1 through all their compositions. And similarly for the pinkish set down here. What we want is that we can also go from this address G to the address GH using a composition of generators that carry both A1 and A2. Right? So you would like that this H can also be represented as a sequence of generators, or as a composition of a sequence of generators that carry both elements simultaneously, because then you don't have this problem. Then, being a composition of partial isomorphisms, they would carry an arrow from A1 to A2, say, into an arrow from B1 to B2. Right? So what we want is no hole here. Right? What this condition here says is really just that you could also go in the intersection of these two generator sets and arrive in the same destination. Right? And this is just avoiding a certain two-cycle formed by cosets. Right? And this is why coset acyclicity matters. And for the rest of this talk, I just have to give you a quick run through of the results that can be obtained in this direction in terms of existence of such nicely behaved finite groupoids, and uses, well, a very brief glimpse of different uses that have already been made of this. So first of all, you can, in a combinatorial and rather non-trivial construction, produce groupoids that are as good as you like in this sense, namely, for any threshold for the length of coset cycles that you want to avoid, capital N there, and for any underlying sort of pattern of sorts and links, as in the overlap specification, there are finite groupoids of this type that do avoid all coset cycles of length up to N. Right? In particular, you can get rid of 2 cycles of cosets and thereby overcome any difficulties with respect to global inconsistencies in these gluing processes. Right? And the idea, well, maybe I shouldn't go into this, but this is sort of a rather complicated interleaving of combinatorial group actions on certain partial amalgams of subgroups or calligraphs of subgroups, etc. And you have to work rather hard to get this. So this is why the paper is long. As a corollary, we get really that this proposal to put such amalgamation constructions on a background structure that is a well-behaved, nice groupoid of this kind, that this always works. And you can actually achieve realizations in the way that I advertised that respect all the symmetries of the input structure, so that you don't make any arbitrary choices anywhere in the construction. That is sort of a nice feature of genericity. And that you have any desired degree of local acyclicity in terms of overlapping copies of the structures that you glue together. Right? So locally, in terms of just not too large portions of the final result, you will not see any cycles if you don't like them. And you have local tree decomposability in terms of the patches that were glued together. Right, so in this sense, it's generic and at least locally free. Of course, it can't be totally free because that necessarily makes it infinite if you started from a cyclic pattern initially. Now, some applications. And the first one is really one where you don't even start from a sort of an arbitrary overlap specification of the kind that I outlined in the beginning, but you start from a realization of an overlap pattern, namely an actual hypergraph. If you have a finite hypergraph, maybe stemming from a relational structure, what have you, then you can, with this construction, abstract its overlap pattern and then produce realizations of the same overlap pattern that avoid all cycles of hyperedges up to a certain length. So these are acyclic, so-and-so acyclic, n-acyclic hypergraph coverings that you obtain in a finite manner. And it's this kind of hypergraph coverings that actually play a great role in these characterization results where you want to play games, because locally you can make things acyclic for, say, the analysis of the finite model theory of guarded fragments and things like that, where the hyperedges are the guarded patches that need to fit together in a nice way, but shouldn't form short cycles that would be detectable in a first-order Ehrenfreund-Tricet game, say. Okay, another one, which I mean that thing is actually what brought me to this whole problem of producing amalgams of the right acyclicity behavior. The other things that I'm mentioning here, especially, came out as a surprise that you can actually deal with rather interesting results on the extension of local to global symmetries using exactly those same nice groupoid constructions. So this EPPA stands for extension property for partial automorphisms, and the problem is maybe best explained in terms of this sketch. You're given a finite relational structure A together with some collection, and here I put a single internal partial isomorphism of this structure. And the task is to find an extension which is still finite, structure B, so that the original A sits as an induced substructure, and in such a way that this local symmetry that you have inside A extends to global symmetry of B. Right? Now, what does that have to do with overlap realizations in the way that I talked about so far? Well, obviously, if you think of extending this partial isomorphism that you have internally to A, that means it carries a whole copy of A that's fixed to this part, to that thing here. You get another copy of A, so you keep adding copies of A that need to overlap according to the behavior of the partial isomorphisms that you want to realize and turn into global symmetries. Right, so here we obtain actually as a corollary of the construction that I sketched. For any finite structure A and any collection of partial automorphisms of that structure, an extension that is really just obtained from gluing pieces or copies of A according to the identifications that are necessitated by the partial isomorphisms, the given partial isomorphisms, and make this so symmetric as to really solve this EPPA question, and also to make it as acyclic in terms of the pattern that the overlapping copies of A make out in this overall in the structure B as you like. So you can make things such that the atlas of A charts that you just get by the automorphic images of the copies of the original structure A form an n-acyclic hypergraph in the sense that small size n sub-hypergraphs are actually acyclic, tree decomposable, nicely behaved. And therefore, the construction is locally free and universal. If you look at only small pieces, then it's really tree-like, the realization that you get. and therefore remains universal with respect to homomorphisms. And this is interesting because the strongest of the results that you have up here is one that is a conditional statement, and it works within a class of structures with some set of forbidden homomorphisms. So you forbid certain configurations in the target structures and of course in the given input structure A, and then the statement has to be turned into a finite model property that says if you have any solution, any such extension that extends the given partial symmetries to global automorphisms of a structure that doesn't realize the forbidden configurations, then you have a finite solution of this kind. But this is what comes out here, just because locally and in terms of finite controlled areas, you are as generic and as free as the free construction would be infinite anyway. Right? So we get the full strength of this finite model theory, finite model property version, this conditional statement on extension properties for partial isomorphisms from the nice, well-behaved nature of the realizations that come out from this groupoid construction. Right, and then this has various uses in modal and guarded logic, some of which were already briefly referred to in Eric's talk this morning. Finite model properties and finite controllability questions for guarded logics and some of their relatives can be treated if you subject the corresponding models or plans for building models to this kind of generic realization that avoids short cycles. Right? Because cycles, apart from multiplicities, are the big things that you can't control with guarded assertions or, say, tuple generating dependencies and things like that. And therefore, you need to smooth things out with respect to short cycles. You want to avoid them, and to boost multiplicities, which is always easy. But in this way, this is a major tool in characterization theorems that work both classically and in the sense of finite model theory for the guarded fragment and some of its extensions and relatives that have recently been studied, including the guarded negation fragment that Erich mentioned, which is one of the sort of the biggest nicely behaved fragments of first order logic in this family that we now have. And what I want to say here, well, that's been covered in some sense, but here another class of characterization theorems that work for modal logics extended by non-first order constructors like common knowledge operator, where you have a fixed point like construction in the background, which sort of clearly seems to belong in the remit of monadic second order logic, but in a sort of tame fragment of that, of course. And it turns out that you can use these Cayley groups, in this case even groups, you don't have to go to groupoids for that application, and use the structural analysis that's being suggested by the way that these models are generated systematically from a set of generators and of controlled coset acyclicity in order to play N-Feucht-Feucht games here in a domain that's a challenge because it really goes beyond first order logic and a little bit in the direction of monadic second order logic. Okay, so I think I should stop here, but here are some related references that range from applications to the guarded fragment on, for instance, the guarded negation fragment, to a nice discussion of the concept of guarded by simulation in an older paper with Erich. A very old thing on conformal hypergraph covers that I didn't mention explicitly, but so basically the work that I'm talking here about here now includes the results that we obtained there, which could only deal with one aspect of acyclicity in hypergraphs, and now with the limitations have been overcome. Then this Herwig-Laskar theorem that I mentioned, this EPPA result that can be reproduced here. And the technical source for all of this is the last one, which is on arXiv, but the better version is the more current version on my homepage. Thank you.
Okay, questions? Well, I'll ask a quick question. So, if you wanted to apply this to, for example, to get finite models of the extension axioms for graphs, the random graph theory, like, could it possibly help you to do this?
Oh, this is an interesting suggestion. I've not thought of that. I mean, this is part of the hope that all of you have nice ideas where else this could be applied, because it really has turned out to be a tool that seems to solve many more tasks than the one it was designed for. But I've not looked into that specifically. No. Thank you.
So have you thought about using it to characterize order in a P?
No. No, I mean, of course, you see, you have to have an environment, or the problem needs to arise in a situation where you don't worry about producing more copies of things, right? So where you can't count in some sense, don't have control of multiplicities. And in fact, it's a way to overcome the inability to deal with multiplicities, to determine them. Therefore, you need to make them large so that large enough is indistinguishable again. Right? So in some sense, it's going in the opposite direction. I mean, it doesn't help to analyze concrete structures, because here you want to use an incredible freedom of unfolding things locally to any degree you like, but keep it finite. So finite is the only thing that I can guarantee. Sizes, for instance, are awful in all of this, right? I mean, these very generic groupoids that I obtain there must necessarily be incredibly large, and it would sort of blow up anything that would come into sort of a reasonable complexity consideration.
Let me say where I'm coming from.
Yeah.
Anyway, it's probably impossible. But I want to describe the sort of generic, you give me a structure, I want to describe the generic structure in some format, so that and then maybe there's some description of it that you can take and compute on that rather than on your original thing. So somehow you're building a canonical estimate of the original.
Mm-hmm. Possibly, yes. I mean, of course, similar amalgamation things occur a lot when you go to Freycinet limits, etc. And what one could ask, in which situations do you actually realize some of the properties of the limit in sufficiently large finite approximations? But that's something that I haven't explored either.
That is what we have in mind, Cherlin's problem about the finite model theory of the extension axioms for triangle-free graphs.
My problem is the one for distances, actually. I asked the same problem for the finite model property with graphs with distance operators, and there's no known construction of that in any way. And so in doing this, you might even have an experimental way to try to get, possibly finite models of very simple kind of those axioms. That's really what I was
in terms of it, just because you mentioned sort of acyclicity criteria. It's open as far as I know, and a very interesting open problem that I would have hoped to solve with this, but so far I don't see how, to do this Herwig-Lasker type of extension property for, say, 4-cycle-free graphs. For 3-cycle-free, we can do it here, but because 3 cycles are clique, I mean, they're not really cycles. And for 4-cycle-free...
But it's open if the theory has the finite model property, right? That's
yeah, but I'm talking about this extension property for partial isomorphisms. Whoops, why does this? Has this been deactivated? Or no, I switched it off maybe inadvertently. But I mean, in this sense here, the conditional statement that if you have a solution that is 4-cycle-free, though infinite, then you will have a 4-cycle-free finite solution. Finite solution for the extension task. And this is not a model of any obvious theory that you would put, but a combinatorial task which has this kind of finite model property.
Chris, how much fat is in your construction?
How much, sorry?
Fat.
Fat?
So you say sizes are awful.
Yeah.
But it was too quickly to understand, but it looks like they have to be so awful.
Yeah, actually, we're looking into this. I mean, I don't have any really good lower bounds. But the construction, of course, is such that the groupoids that I produce here are sort of off-the-shelf solvers for any such problem, right? So, of course, in many cases, you really want to look at, say, coset cycles that are formed by very specific kinds of cosets, not arbitrary combinations of generators. But the construction that I have would really sort of solve any such problem equally well and at equally tremendous cost. in one go. Right? So you don't actually look into the actual, say, topology of the structures at hand, or the way in which they need to be linked. It's just sort of in terms of numbers of generators and how many different sites labels you have, and up to that, it's sort of generic also in terms of the machinery that I'm using.
Thanks very much.